Hello all. So we move on to the part 2 of lecture 1. Here we'll be seeing this next half of fourth module. The topics being covered in this presentation are three-phase voltage source inverter, square wave as well as PWM operation. So first we'll be dealing with square wave operation of three-phase voltage source inverter under mode 180. So here you can see I have a three-phase inverter feeding a balanced star connected three-phase load. The 6 switches of the inverter are named from S1 to S6. The naming of the switches is in the order in which they are going to conduct, and they are fed from a constant voltage source VDC. Now, before moving on to the operation of this inverter, there are certain rules we have to keep in mind. The first rule is the switches of the same phase or the same leg should not be turned on together. That is, S1 and S4 will not conduct together. Similarly, S3 and S6 should not be turned on together. S5 and S2 should not be turned on together. The second rule is each switch is turned on for 180 degree. That is, the switching cycle of the 6 switches is shown here. From the figure you can see each switch is kept on for a duration of 180 degree. Here at 0 S1 is turned on and it remains on up to 180 degree. Similarly S4 is turned on at 180 and it is kept on till 360. Similarly for all the other switches. The first rule is also satisfied in this switching sequence. If you look at the figure, S1 is kept on for 180 degree and only after S1 turns off at 180 will S4 take over. S4 remains on for 180 and only after S4 is turned off, S1 will take over. Similarly for phase B switches S3, S6 and phase C switches S5 and S2. The next rule is the switches in the upper group conduct at an interval of 120 degree. That is, if you look at S1 is turned on at 0 degree. The next one, phase B switch S3, will be turned on 120 degree after S1 starts conducting, that is at this point. Similarly, the next switch, phase C switch S5, is turned on 120 degree after S3 starts conducting, that is at 240. So among the upper 3 switches, there is an interval of 120 degree. So S1 starts at 0 degree, S3 starts at 120, S5 starts at 240. And the last rule is switching takes place every 60 degree. That is, if you look at the figure, at a time 3 switches are conducting. From 0 to 60 degree, S1, S6 and S5 is on. That combination remains for a duration of 60 degree. At 60, S5 is turned off, S2 is turned on. So now the new combination is S1, S6 and S2. This combination remains for the next 60 degree. So at 120, S6 is turned off and S3 takes over. So S1, S3, S2 is the next combination. Like that, for every 60 degree, one switching takes place. That is, only one switch among the 3 phases will undergo a transition. But anyway, at a time, only 3 switches will be turned on. Next we move on to the analysis of the 3-phase voltage source inverter. The thing you have to keep in mind is the current coming from the source enters the load through the upper switches and leaves the load back to the source through the lower switches. So consider the first duration, that is from 0 to 60 degree. Switches S1, S6 and S5 are conducting. Here S1 and S6 are the upper switches which constitutes phase A and C, and S5 is the lower switch constituting phase B. Therefore, phase A and C will be in parallel and the parallel combination will be in series with the lower one, which is phase B. So current enters the load through phase A and C and leaves the load through phase B. Now, the effective impedance of this parallel combination will be Z by 2 and the total current coming from the source I can be calculated using Ohm's law, and it comes to 2 by 3 times VDC by Z. After calculating the current coming from the source, we can calculate the phase voltages VAN, VBN and VCN, that is voltage across each of these impedances. Since A and C are in parallel, the voltages will be equal. So that is equal to, again using Ohm's law, I into the effective impedance of these two, which is Z by 2. It comes to 1 by 3 times VDC. Similarly, the voltage across the lower impedance VNB. VNB means the voltage of point N with respect to point B will be I into the corresponding impedance Z. So that comes to 2 by 3 times VDC. But the phase voltage we are interested in is VBN, that is the point B with respect to N. Therefore, it comes to minus 2 by 3 times VDC. Now consider the next 60 degree interval, that is from 60 to 120 degree. The switches conducting are S1, S6 and S2. So here one upper switch and two lower switches are conducting. So the current enters the load through phase A through switch S1 and leaves the load through phases B and C through the switches S6 and S2. So again, as in the previous case, we calculate the current, which remains the same, which is 2 by 3 times VDC by Z. Again, we calculate the phase voltages or the line to neutral voltages. So the same method can be adopted here. So the phase voltage VAN will come to I into Z, which is 2 by 3 times VDC. Similarly, here we will be calculating the phase voltages VBN and VCN. It comes to minus 1 by 3 times VDC. Similarly, we can calculate the phase voltages for all the switching states starting from 0 to 360 degree, which is tabulated here. Once the phase voltages are determined, we can move on to the line voltages, which is determined using the formula VAB is VAN minus VBN, VBC is VBN minus VCN, and VCA is VCN minus VAN. Consider the first duration 0 to 60 degree. VAB is VAN minus VBN, which is calculated as VDC. Similarly, VBC is equal to VBN minus VCN, which comes to minus VDC, and the last one VCA is calculated to be 0. So for all the switching states from 0 to 360, we also calculate the line voltages, which is also tabulated here. With the help of the tabular column, now we can sketch the waveforms for the three phase voltages VAN, VBN and VCN. Consider the first 60 degree. From 0 to 60 degree, we had calculated the value of VAN, VBN and VCN. So VAN comes to 1 by 3 VDC, VBN minus 2 by 3 VDC and VCN 1 by 3 VDC. The same has been plotted in the figure. The next 60 degree, VAN, VBN and VCN has been calculated. The same has been plotted. From 120 to 180 degree, VAN is 1 by 3 VDC, VBN is also 1 by 3 VDC and VCN is minus 2 by 3 VDC. So you can see the same has been plotted in the figure. In this manner, by referring to the tabular column, you can update the waveforms for the phase voltages for several cycles. Similarly, we can also sketch the line voltages by referring to the tabular column. So in line voltages, you can see the value attained by the line voltage is either plus VDC, minus VDC or 0. Hence, this inverter is also known as a 3-step inverter because the line voltage attains only 3 steps, that is plus VDC, 0 and minus VDC. Next, we move on to a 3-phase sine PWM inverter. If you look at the output voltage waveform of a 3-phase voltage source inverter under square wave operation, we can see we are getting a square waveform at the output. which is not the actual desired output voltage waveform. For any inverter, for common applications, we prefer a sine wave at the output. So to get a waveform which is closer to a sine wave, we apply PWM method, which helps in both eliminating the harmonics as well as we get a waveform which is more closer to a sine wave. Now the logic used in sine PWM inverter for a three-phase operation is same as that of single phase. The only difference is here there are three control signals, one for each phase. So V control A is the sine wave used to control the phase A switches S1 and S4. V control B is used to control the phase B switches S3 and S6. Similarly, V control C is used to control the phase C switches S5 and S2. The logic used is also somewhat similar. That is, the control signals are compared with a high frequency triangular wave to generate the switching pulses for the corresponding phases. So if V control A is greater than V triangle, the phase A upper switch S1 is turned on, and if V control A is less than V triangle, the lower switch of phase A S4 is turned on. Similarly, for phase B, if V control B is greater than V triangle, S3 is on, else S6 is on. For phase C, if V control of phase C is greater than V triangle, S5 is on, else S2 is on. Now if the upper switch is on, the corresponding phase voltage will be plus VDC, and if the lower switch is on, the corresponding phase voltage will be 0. So if you consider the phase A voltage, the waveform is shown here. From this point to this point, V control is greater than V triangle. Therefore, VAN, the phase voltage of phase A, will be plus VDC. And from this point to this point, V control is less than V triangle. So the lower switch is on. So VAN will be 0. Similarly, we can obtain the waveform of VBN by comparing V control B and the triangular waveform. For convenience, only phase A and phase B is shown here. Now once you get the phase voltages, we can also obtain the line voltage using the same formula, VAB equal to VAN minus VBN. So for each point, compare these two waveforms, you can obtain the voltage waveform of the line voltage VAB. Similarly, the other line voltages can also be obtained using these formulas. Now, the fundamental component of this waveform will be a sine wave of 50 Hz frequency and desired amplitude. And finally, the peak value of the fundamental component of the phase voltage of phase A, VAN1. 1 correspond to fundamental component is, experimentally it has been determined to be MA times VDC by 2, where MA is the amplitude modulation index. If you recollect, for single phase inverter, the value was MA into VDC. For three phase, it has come to MA into VDC by 2. So that is the difference here. Now once you get the phase voltage, for star connected load, the value of line voltage will be into root 3 times the phase voltage. Therefore, the line to line voltage is root 3 into MA into VDC by 2, and the RMS value will be peak value by root 2. Therefore, the RMS value of line to line voltage of phase A, VAB1, is root 3 by root 2 times MA into VDC by 2, which comes to 0.612 times MA into VDC. So with this, we are winding up with 4th module. Thank you.